Question 4 from the multiple choice of the 2024 Higher Physics examination from the SQA. A ball is thrown horizontally over the edge of a cliff. A group of students draw 3 velocity time graphs, VT graphs, to represent the motion of the ball when air resistance is taken into account. And as your 3 graphs here, graph X, graph Y and graph Z. Which row in the table shows the graphs that represent the horizontal component of the velocity and the vertical component of the velocity? Well, we recap our National 5 horizontal projectiles without air resistance. You'd get a series of graphs like this. You get the horizontal velocity graph, that's the top one, and the velocity would not change, it'd be constant throughout the motion. The vertical velocity graph, that's this graph here at the bottom, you can see the velocity is going to increase in accordance with the acceleration due to the force of gravity. The velocity is positive in this case because we're taking the velocity downwards as positive to make the graph look like that. So that's a situation where we have no air resistance. Now let's go to a simulation where we have air resistance. I'll drag this over here and you can see the projectile launched off the cliff, and you can see the graph is definitely the vertical component is bending and the horizontal component is bending slightly down. And that's all because air resistance is really proportional to the velocity of the object. So the faster the object goes, the more air resistance that the object is going to receive. So you can see that the vertical velocity is bending down the way like this, and the horizontal one is bending down as well. So what's the 2 contenders? The 2 contenders for this particular question is that the horizontal velocity should bend down the way. So this one's going to be the horizontal velocity, this one here, as we saw on the simulation. The horizontal velocity with air resistance is going to gradually reduce the velocity because the air resistance is opposing the motion. Now what about the vertical velocity? We can see it's going to be this one here. The vertical velocity starts off and the vertical velocity is going to be reduced as the time goes on. So this is the vertical velocity component graph. And you can see this graph here is heading towards a kind of levelling out, and that would be the terminal velocity. So that's a big clue as well. So that's the answer. It's going to be 4. Graph X is the horizontal and graph Y is going to be the vertical component of the velocity. So just one little final look at that Vpython simulation with air resistance of a projectile off a cliff, and you can see definitely that the vertical velocity is bending away and the horizontal component velocity is also being reduced from that straight line. Have a look at that for a couple of seconds. You can see with what happens with air resistance taking place. There we go, the vertical velocity one definitely bending down and the horizontal one dipping down as well. Question 5 from the 2024 multiple choice paper in physics. In a hydroelectric power station, water flows from a reservoir through turbines at the rate of 4.5 times 10 to the power 6 kilograms per minute. The reservoir is 150 metres above the turbines, and we have to calculate the total power delivered by the water in flowing from the reservoir to the turbines. Here's a quick sketch of what we have. You can see we've got 4.5 times 10 to the power 6 kilograms of water, and it's a height 150 metres. That's the reservoir there, and it's going to fall down onto this turbines here. It's really an energy problem. Per minute, we'll keep that in the back of our mind at the moment and just simply work out the potential energy which the water has at this point here. That potential energy is going to be transferred into kinetic energy at the turbines. So let's work out the potential energy of that amount of water. So the potential energy is quite simple to do. It is equal to the mass times the gravity times the height. So we've got a mass of water equal to 4.5 times 10 to the power 6 kilograms multiplied by the gravitational field strength 9.8 and multiplied by the height, which is above the reference point, which is the turbines here. It's going to be a height of 150 metres. So if we work that out in our calculators, we end up with a value of 6.165 times 10 to the power 9 joules. So that's the amount of energy going to be transferred into the turbines due to conservation of energy. But we want to know the rate of that, and we know that the power is the rate of energy transfer. It's just simply equal to the energy transfer divided by the time it took to transfer it. So we're going to have 4.5 times 10 to the power 6 kilograms of water per minute hitting this turbine here. So that's going to be the time we have to use. So the energy transferred is 6.165 times 10 to the power 9 joules, and we have to divide that by 1 minute, which is 60 seconds. And then we get our joules per second, which is equal to the watt. So we do that in my calculation, we get 1.10 times 10 to the power 8 watts, or joules per second. And the answer to that is going to be 1.1 times 10 to the power 8 watts. And there's the answer there. It's going to be C. Question 6 from the multiple choice paper. 2 trolleys move along a level bench as shown. The trolleys collide and stick together, and they continue to move along the bench. And you can see the data of the trolleys there. Both are moving from left to right, and they have a mass of 2 kilograms travelling at 5 meters per second, and the other trolley is 6 kilograms travelling at 1 meters per second. And after the collision, they're going to stick together. So the first thing you do is draw a quick sketch of that. Here's my quick sketch here. And then you fill in all the details about those 2 trolleys. Well, we know it's going to have a mass of 2 kilograms for the first trolley, and it's going to be moving with a velocity of 5 meters per second. 5 meters per second. This second trolley here has got a mass of 6 kilograms, and it's going to be moving with a velocity of 1.0 meters per second. After the collision, they're going to stick together. It's going to have a total mass of 8 kilograms. And we don't know the speed v, but we'll find it out. We don't know which direction it is either. We trust in the mathematics of a momentum calculation. So we know that momentum P equals mv, mass times velocity. So we work out the momentum for each one of these. And the momentum, the first one is going to be mass, 2 times the velocity, 5. And the momentum of this one is going to be 6 times the velocity 1, all going from left to right, so all velocities are positive. 2 5s are 10, 6 1s are 6, and we can say the total momentum before this collision is going to equal to 16 units of momentum, which we know is going to be 16 kilograms meters per second to the minus 1. After the collision, you can see the total momentum after is going to be just simply the mass times the velocity, and it's going to be equal to 8v. Now we use our conservation momentum. We say that the total momentum after the collision should always equal to the total momentum before the collision. That's providing there's no external forces acting on the system. So we have total momentum afterwards is going to be 8v, and that should be equal to 16 in terms of the units. So 8v equals 16 implies that v is going to equal to 16 divided by 8, and you're going to have v equal to 2 meters per second. That is going to be the velocity of this trolley. It's a positive number, so the trolley is going to move in that direction there. So the answer to this question is the trolley is going to move at 2 meters per second to the right, and that's going to give you this answer here. It's going to be C.